we are moving to the next panel, which is on scientific breakthrough enabled by quantum tools. And it's my very great pleasure to introduce the three panelists for today. Unfortunately, Nergis introduced me this morning, so now I'm going to do a very bad job in introducing her. So I cannot accomplish what she can do. But our first speaker is going to be Nergis Mavalvala, who is the Marble Professor of Astrophysics of MIT and also the Dean of Science. And she's been really a great supporter of QMate, so thank you again. Nergis has been a long-time member of the Laser Interferometry Gravitational Wave Observatory, or LIGO, much easier to say, that announced in 2016 the first discovery made just a year before of a gravitational wave. She received her undergrad degree from Wesley and a PhD from MIT, so we have a lot of great alumni around. And she had many, many awards. I will spend the rest of the day if I list them all, but I want to remember at least the MacArthur Award, and also I think an award for the best teacher in undergrad, which I think it's also very, very important, not only research, but many other things. And Nergis has not only contributed to the discovery of gravitational waves, but she has also made my life much, much easier. Every time that I need to introduce quantum sensing, which is what I work on mainly, I can just point to Nergis' work and say, you see, this is where quantum advantage is already being used. Forget about quantum computer. We will get real quantum advantage for a practical purpose at some point. In sensing, we already have it. It's really being used to sense gravitational waves coming from black holes, which are so far away that without the quantum advantage, we would not have been able to see. So thanks, Nergis. The second speaker is going to be Vladan Vuletic, who is the Lester Wolf Professor of Physics and is also currently the director for Center for Ultra-Cold Atom and also a co-founder of QuEra that we will hear more about in a later panel. Vladan is an atomic physicist who has a very broad interest in quantum precision metrology, quantum control of atomic systems, cavity QAD, and really is bringing together this technology for practical purposes, both in precision metrology and in quantum computation. He did his studies in Germany, getting a PhD from Munich, and then he moved for a postdoc at Stanford, where he also started as an assistant professor, but luckily we managed to bring him here, and I'm very happy that he's been here and that he's been sharing Building 26 with me. And I'm also grateful to Vladan because he keeps me in shape. He told me once that every time the elevator in 26 goes up and down, his experiment can sense it. And so from that point on, okay, when I bring my bike up, I use the elevator, sorry. But otherwise, I take the stairs. And if you are in 26, I encourage everybody of you to just take the stairs. It's good for you. It's good for the experiment. And that's because Vlada makes experiments which are so precise that really they can sense when a big chunk of metal goes up and down. And it's really going to talk to us how making this very precise quantum machine can really help you in make some new scientific discoveries. So the last speaker of the session is Daniel Harlow, who's an associate professor of physics. And he is a theoretical physicist who's been working on black holes. And you could think, okay, what have black hole to do with quantum? Well, actually, they have a lot to do with quantum. And what he's really working on is really trying to understand how we can connect quantum mechanics to the theory of gravity. And quantum information science has a really important role there. And Daniel obtained his undergrad in Columbia University and then a PhD in Stanford, but another person that we stole from Stanford came here as a faculty back in 2017. And like everybody else in this panel has earned so many awards. Sorry, Vladan, I forgot to mention all of yours. Okay, he's like, I forget it. But one of the latest for Daniel has been the New Horizon in Physics Prize. So this is, I think, very, very important. We heard in the first panel how people in the quantum industry are working really, really hard to try to make their device fault tolerance using quantum error correction. And instead, what Dan is trying to do is to use quantum correction to understand black holes. So easy things, of course. So with this, I will stop here, and I'll let Nergis take the podium.
I'm even shorter. So hi, everybody. Actually, is my mic work? Then I'll just come here. Great. So it's a pleasure to be here. I'm going to spend just a few minutes telling you about a quantum technology that has really opened a new window to the universe, which is it has allowed us to listen to gravitational waves that come to us from cosmic distances. I speak on behalf of my group here at MIT, the LIGO group at MIT, but also for all of our collaborations across LIGO, Virgo, and Kagra. So let me just start my story at a more recent event in the field, which was the 2017 Nobel Prize in Physics, which was awarded to Professor Rainer Weiss of MIT, who just passed away a couple of months ago, sadly. One half of the Nobel Prize went to him, and a quarter each to Professors Barry Barish and Kip Thorne at Caltech. And this was for the discovery of gravitational waves using an instrument called a LIGO, which was in fact the brainchild of Weiss and Thorne in the 1970s. Now, what was this Nobel Prize given for? It was given for this observation, if you will. This is the very first detection of gravitational waves from two black holes that collide. And what you see on the screen there as the graphic is a time series of the gravitational wave strain, which is literally the ripples of space-time as measured in our instrument on a time scale of a few hundred milliseconds. And the importance of this discovery was manifold. It was the very first time we saw directly these gravitational waves. It was the very first time the instrument LIGO made those detections. The amplitude of the wave turns out to be about 10 to the minus 21. Kip Thorne told us in the late 1960s that that's what we should expect from black holes at a distance not too far from us. Ray Weiss in the early 1970s designed the instruments that later became LIGO, and already in the early 1970s, he had told us that we would need to measure these displacements at the level of 4 times 10 to the minus 18 meters. Now, in the earliest conceptions of these instruments, they were not very quantum mechanical, even though you would have expected them to be for reaching that kind of precision. I'm going to say one other thing about this very first discovery, GW 150914, which I'm going to come back to. These were gravitational waves from black holes that are about 30 times the mass of our sun and about 1 billion light years away. And that's something that you're going to remember, because I'm going to come to another system 10 years later with about the same properties. So since the first discovery, and in the 10 years that have passed since 2015, we've seen about more than 300 astrophysical observations. And those have been made by a series of observatories that I've drawn on the right there. The two at the top are LIGO. These are optical interferometers. These are laser interferometers. They're L-shaped instruments in which light beams go down 2 paths that are 4 kilometers long. They interfere on the beam splitter, and we measure the phase shift of the light as a measure of the displacement of the mirrors due to the passing gravitational waves. They're kilometers long because that's the scale you need to reach the precision that we have. Now, these the observatories, the two LIGOs, Virgo in Europe and Kagra in Japan, all operate with periods of making astrophysical observations, and then periods of instrument improvements, and then periods of astrophysical observations. And this map of discoveries, the very first were only 3 in observing run 1, then about 6 in observing run 2, and Then observing run 3, there were a couple of dozen. And then in observing run 4, which just ended a few weeks ago, there have been many dozens. Now, a more visual way of looking at this rate of discoveries of these kinds of black holes and neutron star systems that we've seen so far is this graphic here, which kind of shows you that this is a cumulative rate of observations. And what you should pay attention to is the change in slope between the observing runs. Between observing run 1 and 2, we were seeing something on the order of 1 event per month. And then starting observing run 3, and certainly in 4, we're seeing something on the order of several, more than 1 per week, so 5 or 6 per month. And there has been one technology that has given us the lion's share of the instrument improvements that lead us to this higher rate of doing astrophysical observations, and that is a quantum technology called squeeze light. And so let me just tell you a little, let me show you 2 things. Remember I told you that very first observation we saw, that's the top curve. Earlier this year, in January this year, we saw another black hole system with more or less the same parameters, 30 solar mass black holes colliding at about 1 billion light years away. And the difference between these 2 signals, you can see in the purple of the data, is that the first observations we saw had a signal-to-noise ratio of about 25. And now, 10 years later, we see a similar system with a signal-to-noise ratio of about 80. And the improvements in the instrument come from a technology called squeeze light. So I'm going to just show you a quick view of how quantum noise works. Vacuum fluctuations, which we in the quantum world are very used to, are the culprit here. So we have an interferometer. The laser light interferes at splits at the beam splitter, hits the 2 mirrors at the ends, reflects back, and we measure the interference pattern at the output. Now, the open port of the interferometer, which is the bottom output port, is an opening from which vacuum fluctuations can enter. And what we show here is a phase space representation of those vacuum fluctuations, which is simply that you have an uncertainty in your electromagnetic field centered around the origin because it's a vacuum. It has no coherent amplitude. Now, for the same reason that the laser light goes back towards the laser because we've arranged the phase of the 2 arms, anything that enters that open port comes back at the open port. And now if you have a gravitational wave that comes by, which is the yellow phasor that you see there due to the displacement of the mirrors in the arms, it superposes with that vacuum state, and that gives rise to the thing that we all see in our labs all the time, shot noise. That is the quantum fluctuations of the light that we measure on a photodetector. Now, amazingly, these same vacuum fluctuations also give us another kind of noise, which we don't often contend with in our labs, and that is that those same vacuum fluctuations also superpose with the bright field that's hitting the mirrors, and those fluctuations then kick the mirrors, and that is called radiation pressure noise. The fluctuations on the light are kicking the positions of the mirrors, and that is also something that would be a problem in something like LIGO because we measure the positions of the mirrors to measure the signal of the gravitational waves. So if you could then engineer your input light to look like a squeeze state, so in this case, it's essentially that round fuzzball of uncertainty turned into an ellipse, such that the area of the ellipse is the same as the area, or at least not smaller than the area of the circle, because that would violate Heisenberg's uncertainty principle. Then what you would see is your squeezed vacuum state would superpose with your signal phasor, the little yellow arrow, and you could make a measurement that's better than what the pure vacuum state would allow you to do. So you carefully engineer a state of light that you put into your interferometer so that the narrowest part of the ellipse, so the least noisy part of the phase space, superposes with your signal, and you should be able to do better. And this was an idea that was given to us in the early 1980s by Carl Caves. And now fast forward to LIGO's observing run 3 right around 2018, 2019. And what you see is these curves. So we built a squeeze light source. I'm going to tell you very little about it. It's on the left. in the graphic. What it is essentially is a nonlinear optical system that can take light and can rearrange the fluctuations between the amplitude and phase properties of the light. What's more interesting is that the black curve on the right is the sensitivity of advanced LIGO used during observing run 3. And all you see is it's a spectrum. It's a frequency on the horizontal axis and the amplitude of the wave on the vertical axis. Black was when you have no squeezing. Green is when you introduce a squeeze state. As you can see, lower is better. You have less noise, and that was the improvement in the instrument that we made during observing run 3. Now, if you look carefully at low frequencies, green goes above black, which means that your squeezing is actually hurting you. That was the radiation pressure noise, and that comes from the long part of the ellipse affecting your measurement. So we then built a system that would allow us to rotate that squeezing ellipse as a function of frequency, and this is the thing I want you to pay most attention to. Black curve is, again, unsqueezed, and then the purple curve is what we get with this new rotated squeezing ellipse, and you see 6 dB or a factor of 2. And if you ask, what does quantum advantage look like? That's what it looks like. The gap between the black curve and the purple curve is the quantum advantage that we're seeing. So I'm going to just finish my talk with saying that these gravitational wave detectors are exquisite quantum sensors. In our group at MIT, we're now making squeeze light sources for other applications. And I just want to end with many thanks to members of the LIGO, Virgo, and Kagra teams, and to all of the members of my group. Thank you.
Good afternoon, everybody. I would like to tell you about scientific frontiers in quantum physics. There are a number of scientific frontiers. One of my favorite ones is what I would like to call the precision frontier. The precision frontier is interesting not only because quantum systems can be exquisite sensors, as we also saw in Nergis's talk, but also that to uncover or release the power of quantum, you have to actually reduce technical and also thermal noise as much as possible. Otherwise, you never see quantum effects, you see just thermal effects. That's why all the systems work at low temperatures. The superconducting qubits use dilution refrigerators to get to low temperatures. We use laser-cooled atoms that go down, in our case, to microkelvin temperatures. So the precision frontier is a very interesting frontier, and I will talk about two subjects. One is entangled atomic clocks, and this connects very nicely to what Nergis has been talking about. And I will show you that actually quantum computers with neutral atoms are not that different in terms of the technology used as from, say, the best neutral atom atomic clocks. And another frontier I probably won't have time to talk about, I'll just show you short movies. I think the AI or machine learning frontier is a very interesting one, where we find in the lab that AI machine learning can now perform experiments significantly better than expert graduate students that have been trained for several years, including me for decades. Let me just go back. Okay, so this is what our atomic clock looks like. It's a number of laser-cooled atoms inside an optical cavity. The optical cavity is there to entangle the atoms and also to read out the state. We have a clock laser that oscillates with the atoms. The atoms oscillate at optical frequencies, so 10 to the 15 times per second, a very high frequency, which gives very high precision. The laser oscillates with them at the same frequency. The laser is a very, very stable laser, not quite as stable as the atoms. And basically, the laser is used to transfer the stability of the atoms to some technological signals that then can be read out and converted to lower frequencies. The atoms themselves are exquisite sensors, even without entanglement. They have very long coherence times. They can be interrogated a long time. They can be trapped in a so-called magic wavelength trap. And the best atomic clocks are now at the level where A, they are limited at by the quantum noise of the atom rather than any technical noise. And B, they can measure, for instance, gravitational redshifts. You may remember that Einstein said that in a gravitational field, clocks run more slowly. This has been first confirmed, with clocks on satellites. Now, with these best experiments, one can measure differences of about 0.1 millimeter. One sees the clocks running at different speeds when one just lifts one of them by a fraction of a millimeter. Another way to characterize these clocks, they are not at 10 to minus 23 yet, they are more at 10 to minus 18. If such a clock ran since the Big Bang, it would be off by about 100 milliseconds or so. So these clocks are sensors, and it's quantum mechanics, just like we have shot noise, just like Nergis has shot noise with photons. When you take a measurement on the atoms give you only one of two outcomes. They are digitized output sensors. And that means that there's noise. If you take 100 atoms and you expect on average 50 to be in one state and 50 to be in the other state, what you see in any given shot is not exactly that. That's only on average. You see noise on that. This is the quantum noise that we're trying to suppress, and that's the quantum noise that Nergis tried to suppress in her system. So here we need to entangle the atoms. We need to create these spooky actions between atoms at a distance. The atoms, we don't like them to collide because we want them to be very good, pristine sensors. So what we use is we use light inside the cavity as a way of transmitting information between the atoms and entangling the atoms. And so the light inside the cavity makes also a squeeze state. In our case, it's a spin state, not a photon state, and we can improve measurements that way. How well can we do? Here's a sequence on the left where we are improving the signal. So on the horizontal axis is an input signal, and on the vertical axis an output signal. The black line indicates the signal when you do nothing, so basically the slope is unity. You get the same output signal as the input signal, but if you do an entanglement procedure and a kind of OTOC-like procedure like Hartmut Neven talked about, so there's an entanglement procedure and a de-entanglement procedure if you want, you can amplify the signal as indicated by the colored curves that have clearly a much bigger slope. And another way for us to think about this is to say that we can take a single measure, can take a single measurement with the entangled atoms, and we can replace 15 measurements with unentangled atoms. So you can make the data acquisition rate, for instance, 15 times faster. So that's a 13 dB or 12 dB enhancement. So these are atoms. The way we like to think about what are the fundamental limits. Here, we have two axes. One is the atom number on the horizontal axis. Many atoms is good because you get higher precision from using more sensors. The vertical axis is the gain that you can get through entanglement. The plot is arranged in such a way that the horizontal line at the bottom of the plot is what you can do with unentangled atoms, the purple line. And the gray region is excluded by the so-called Heisenberg limit that Nergis also mentioned. You can't do better than that, but the goal is basically to go as close as possible to this gray line and high up. The records in absolute spin squeezing were set at Stanford by Mark Kasevich and James Thompson in Boulder. And the red data are our line. And you see we are going parallel to the so-called Heisenberg limits. We are at the distance of about 10 dB, and we think we can continue this line further in future experiments. So, entanglement-induced gain in sensors at least is real and is available. Let's now switch gears and talk about quantum computing. So we use atoms now. Also in light traps, but for the atomic sensors, for the clocks, we use ensembles of atoms, hundreds, thousands, 10,000s of atoms. Here we use individual atoms. And what you see on the screen is not a cartoon. This is actually a picture on a camera where each little green dot constitutes an atom. We trap these atoms in laser beam. There's a pattern of laser beams here that hold the atoms in place. And then we can sort these atoms into grids, for instance, like shown in 2D. So basically, we trap atoms randomly half the time, and then we sort them to make these patterns. We can use these atoms as qubits. We identify two states between which we can create rotations, but we can also induce interactions between them in the form of so-called Rydberg gates. This is basically we bring atoms close and then perform laser excitation to a particular state that acts to do gates. And this is a new technology that has emerged much more recently than say, superconducting qubits. But it's very interesting because it's, as you can already maybe see, it's very scalable. We don't have to fabricate large systems. We essentially have to provide more laser beams to trap and cool. And I'll show you another thing that came about this, became clear this morning, I hope, from the talks when for instance, Hartmut Neven talked about it, that quantum error correction, which maybe even 2 years ago, everybody would have said, not before 2030, 2035, is now has been demonstrated in several labs. It has been demonstrated, as Hartmut showed, in the Google labs with superconducting qubits, but we have also similar results of similar quality in this system. And basically, as you see here, this is a circuit that performs quantum error correction in actually a 4-dimensional hypercube, but because we can move the atoms, we can realize any number of dimensions if you want. And so the microprocessors is by moving the atoms, performing gates. These were the red circles. I will go maybe back, try to run it one more time, to create certain connections and then do quantum error correction codes. And there's a lot of excitement in the field and a lot of questions as well. What are the best codes? What errors can we reach, etc. But I think what Hartmut presented for us, the 10 to minus 6 and beyond logical error rates within the next couple of years are very, very realistic. This is work done at Harvard with Misha Lukin and Markus Greiner. And also Quera is a fund company we founded. This is scaling up to thousands of atoms. Here we are loading continuously atoms and replacing them to keep a quantum state alive between these several thousand qubits on the top. This is a new machine that we are building at MIT, which will be kind of the newest generation neutral atom quantum computing machine. It has 2 regions. One is the upper region where we laser cool the atoms, and then we transport them with laser light into a lower region. I would like to point out that in this system, everything is optical. The read-in of information is optical, the readout of information is optical, and then we rely on commercial devices that transduce electrical signals into optical signals, and very good cameras. And then maybe finally, just as a fun thing, this is something optimized by machine learning. Here we create the Bose-Einstein condensate for the first time by laser cooling. And so I'll play it once again. So the atoms here are trapped and shadow imaged, and then a machine learning program essentially optimized around 50 parameters, and it did, our students were optimizing for a month or so, and overnight the system did it much better, improved by a factor of 6. The time that it took to create the condensate improved the atom number as well. The condensate is this little red dot, and you can see even an atom, what we call an atom laser, maybe shooting out atoms due to gravity downward as the atoms are very cold. So this is another very interesting frontier of how we use AI, not only for maybe decoding quantum computers, but also for more practical purposes like optimizing complex sequences and complex systems. And with that, I would like to thank you for your attention.
Okay. I'm Daniel Harlow. Thanks everyone for listening. I'm going to tell you about black holes and the emergence of space and time. Quantum black holes, it's important. So let's start with a status report on the fundamental laws of nature. So that's my job. If I had a business card, it would say my job is to understand the fundamental laws of nature. So here's where we're at right now. So we've got 2 fundamental theories. There's Einstein's theory of gravity, general relativity, which says that gravity arises from the curvature of space-time sourced by energy and momentum. So since I'm not an experimentalist, I don't have pretty pictures. I'm a theorist, so I have pretty equations instead, okay? So the equations in this talk are art, okay? There's not going to be on the test. They're just beautiful, and this is one of the most beautiful equations, right? Einstein's equation. So on the left-hand side is the curvature of space-time. On the right-hand side is energy and momentum. Okay. So that's one of our theories. Then on the other one we have is called quantum field theory. So that's quantum mechanics for grown-ups. So elementary particles, electrons, neutrinos, etc., are excitations of quantized fields, like the electric field, where causality is protected by saying that at different points in space-time you have independent degrees of freedom. And so here's a Feynman path integral showing you how to do quantum field theory in one line. So that's great. We worked 500 years to get this slide to where it is now. But unfortunately, although both of these theories are good in their own separate regimes of validity, no one has figured out how to combine them in a way that's consistent with everything that we know about the world. And so that's my job, is to try to figure out how to do that. Now, why is it so hard? Why haven't we succeeded, right? We've been working on this a long time. We knew about both of those theories for almost 100 years now. Well, there are various reasons that people give, but I think the deepest is due to Hawking, who argued 50 years ago this year that any quantum theory of black holes that you can find has to violate one of the following sacred principles. So principle number one is that a black hole is a quantum object similar to a chair or an atom with some number of quantum states. And in fact, the entropy, the log of the number of states, is just the area of the surface area of the black hole divided by 4 times Newton's constant. This is, of course, in civilized units where C and h bar are set to 1, and also Boltzmann's constant. Secondly, the formation, evolution, and evaporation of a black hole should be a predictable, which in quantum mechanics means unitary, process, as required by quantum mechanics. And then finally, if you have an observer who falls into a black hole, a large black hole, say like the one in the center of our galaxy, their experience is governed by quantum field theory to all orders in the expansion in Newton's constant. Okay, so what Hawking said, you have to give up one of these 3 things. So in other words, you need to give up on either statistical mechanics, quantum mechanics, or locality. And all of those things sound really important. And that's why the problem is interesting, right? If you have to give up on any one of those things, you're going to learn something deep. Okay, and so that's why we've been fascinated with this problem for 50 years. Now, what can we hope to learn about this using ideas from quantum information theory? Well, the traditional approach to quantum systems, the one that I learned as an undergraduate 20 years ago, is that the way you study quantum systems if you actually want to do calculations is you have to assume that they're weakly interacting, meaning that they're almost classical. They can be a little bit quantum, but not too quantum. If they're too quantum, then you don't know what to do. And when they're almost classical, then we have approximate methods called perturbation theory. Here's an example. This is the leading Feynman diagrams for Compton scattering that we can use, because it's almost classical. On the other hand, if black holes are indeed quantum, as presumably they are since the world is quantum, they have to be strongly interacting. I won't try to convince you of that here in my 10-minute talk, but it's true. And that means that this perturbative method of being close to classical isn't good enough. We need some new methods to figure out how to think about black holes in the quantum regime. Now, I'm a user of quantum information theory, right? It's, I'm an opportunist. Whatever is useful for me, I use it. I use quantum information theory because it's useful to me. And the reason is it gives new ways of thinking about quantum systems that work even when the interactions are strong, even when the systems are far from being classical. So I'll just mention a few of these ideas, right? So one of the first, the one that you heard about a lot already today is these ideas of entropy and entanglement, right? So there's this idea that quantum degrees of freedom can be so correlated with each other that it's beyond any correlation that's possible in classical physics. That's what we mean by entanglement. And then we don't just say it at the level of words, like that sounds kind of cool when you say it with words, but then you can quantify it using ideas like entropy. So that's one of the things. Another thing, which you heard a bit about, is quantum complexity theory, right? This is the question of how hard tasks in quantum systems are to implement, right? Like Peter's thing is he made factoring easier, and that's a statement about quantum complexity. You quantify how hard a state is to prepare, an operation is to do, by counting how many individual operations, say logical gates, you have to do in order to prepare the state or execute the operation. And then there's this idea of quantum error correction, right? So why don't we have quantum computers yet, or at least ones that can do something useful? Well, it's because it's really hard, right? The noise comes in, you just need one stray photon, and oops, you decohered your memory. And so to try to beat that, you have to do something clever like quantum error correction, which I guess John Preskill once described to me as using entanglement to fight entanglement. The way I like to say it is that you protect logical quantum information against noise by storing it non-locally in the entanglement between many physical degrees of freedom, right? So in many of the talks already, we've heard the words logical and physical a lot. Whenever you do quantum error correction, that's what you're thinking about. So in recent years, all of these tools, which none of which were invented to think about black holes. Okay, they were all invented, because to think about how hard it is to do quantum computation, to protect your computer from noise, these very practical tasks that you have to deal with. But it turned out that because these things don't rely on the system being approximately classical, we can use them to learn about things like black holes, even though that's not what they were designed for. So let me just tell you a little bit about that. So here are some of the things that we learned. And there's an asterisk on the word learned here, which I'll mention at the end of the slide. So what did we learn? So the first thing that we learned is that space-time itself, the theater upon which we're all acting out this play that we're in, all the world is a stage, right? But the stage is emergent. It's only there in certain situations and in some approximation. And in more generic configurations of the fundamental degrees of freedom, there is no space-time at all. Okay? And so how do we even begin to think about a theory where that's true? Okay. Well, more precisely, quantum error correction gives us a way to do it. The way we think now, that we've learned to think in the last 10 years, is that space-time, the emergent thing, is really the logical degrees of freedom in an error-correcting code. Space-time emerges from the entanglement between some physical degrees of freedom, I call them qubits here, although they don't have to be, that live at the boundary of space-time. So somehow the boundary of space-time is more real than what's going on in the rest, and everything else emerges from the entanglement between the degrees of freedom at the boundary through the magic of quantum error-correcting codes. And then finally, we learned that errors in the emergence, small mistakes in the encoding of space-time into the fundamental degrees of freedom, can be amplified by doing operations whose complexity is exponential in the entropy of the black hole that you happen to have around. Remember, we're trying to study quantum black holes. So in other words, when you talk about this list of 3 things that Hawking said you can't have, and so I had to modify one of them, the one that ends up getting modified is the third one, the one that said that quantum field theory holds to a good approximation for somebody who falls into a black hole. And the modification from 3 to 3 star is that it only works for operations whose complexity is sub-exponential in the entropy of the black hole. All right. Now here's the caveat. So learned means that we've constructed self-consistent models that work this way, but they're not realistic. But that's okay, I'm a theorist. You guys worry about satisfying your investors in 10 years. I've got centuries to satisfy mine. Okay, so last slide. Where do we go from here? So as a theorist, what I'm really interested in at the moment is understanding what these ideas can teach us about the universe as a whole. If you work on quantum gravity, there are 2 things you study: black holes and cosmology. I've been doing black holes for a while, and now I want to do some cosmology. The other comment I'll make is that, in principle, we can actually explore these ideas in more detail using quantum simulations. Maybe we'll get back to this in the discussion, although I have to confess that if you build something that does quantum simulations, when you've got 10 to the 5 logical qubits, come talk to me. And until then, have fun. Okay, thank you for listening. I will stop here.
Very well, thanks so much for all this very interesting explanation of your scientific breakthrough. So while I will start asking some questions, but if there are questions from the audience, I think we can also potentially get to that. So my first question is actually more of a comment. So we heard a lot from Nergis about beating the quantum noise, and most recently from Daniel about discussing error correction and what that can teach us about black holes. So I want to sort of ask if you had to flip around. So now that you use quantum tools to have scientific breakthrough, can you actually use what you learn to teach to the quantum industry and people working on beating the quantum noise for our purposes, some of the lessons that you learned, and what would you do, both from a technological point of view, from a fundamental scientific point of view? How would you help out?
So look, I think there's no surprise, Paula. Any quantum system, the thing you have to protect against is decoherence. So for us in our optical systems, it's optical losses. And that, of course, has enormous dissipation of any kind, and that has enormous applications for the whole optics industry. Who wouldn't like to conserve their photons, right? And in our case, if they happen to be, such fragile quantum states, then it's even more important. So I think there are certain ways in which the things that bother us in our labs are completely the same. We're looking for the same kinds of gains in how do you protect your fragile quantum states. In terms of where these technologies can go next, so we're certainly thinking in my group about how squeeze states of light, which is what we do, can have impact, for example, in quantum information, or in particular in quantum communication protocols where photons are so important. So that's just one example, but our colleagues will have more.
I mean, I can say certainly, one of the things we've had to do is invent new quantum error correcting codes. And for me, I mean, I don't really care about what do you do with 50 qubits, but I care about what's a code that is a good model for a black hole. And the codes that we've had to invent are different than the codes that have been invented using other methods. And maybe potentially one of them will end up being useful for practical quantum applications. That's kind of how these things go. When you have a source of new ideas that are sort of tangentially related, then these things, if they're good ideas, have a way of sort of cross-fertilizing and ending up somewhere else. That you just wouldn't have thought of if you weren't trying to solve a problem about black holes. Yeah, I mean, it hasn't happened yet, but people are trying. Yeah.
Maybe if I can jump in.
Sure.
I mean, it's a very interesting question to ask. I mean, the quantum systems that are, say, quantum computers are also sensors in the right conditions. And it's very interesting to ask what happens if you combine the two, and what are the most promising ways to combine them. And I know Ike Chuang and others have thought about this. And I think this is a very, very promising avenue because, as you pointed out, Paula, quantum sensors are already showing a quantum advantage. And they would potentially require just a very small quantum computer to enhance that advantage. But it's in ways that we really don't understand at the moment, but which seems very promising.
Still, you sort of discuss with us a little bit about atomic clock and a little bit about quantum computer. If you had to guess the next scientific breakthrough, where would it come from?
Quantum computer, once it works, will be, presumably so much more impactful than most of the other things, because it will be applicable potentially not only to science. I have no doubt that it will revolutionize science, that we will start simulating digitally quantum systems that we don't understand. There's no question at all. But can it solve meaningful classical problems besides reading 25-year-old emails, which we'd rather not do? That's a question, right?
So I think that then you end up a bit provocatively saying, wait until you have how many qubits?
10 to the 5 logical.
10 to the 5 logical qubit. So if you had them, what would you do with that?
If I had them, what would I do with it? Yeah, I mean, it's kind of similar to what Vladin said, right? I mean, to me, what quantum computers are really for is quantum simulation, right? They're for doing science. They run quantum mechanics natively. That's what a quantum computer really is, and that's what you should use it for, at least to get started with. That's where it really has an unfair advantage. Things like factoring and whatever, classical algorithms, that's sort of trying to fit a square peg into a round hole. And sometimes it turns out to work, but it's not so natural. It's hard to predict. I mean, Peter gave us one example, and in 20, 30 years now, we haven't really gotten another one that's as good. But for quantum simulation, it just does it for breakfast. Now that said, right, yeah, why did I want 10 to the 5? It's because the kind of quantum systems that describe black holes that are at least somewhat realistic are systems with large numbers of degrees of freedom. Systems where you really need a decent-sized system to learn something that I don't already know. So you can do things with 10 qubits and say it's a wormhole, but I mean, it's not any wormhole I've ever seen. I don't know. You really need a big system to learn something. So probably I'm not the first thing you do with the quantum simulator. You do the Hubbard model. You do spin systems. You do things that have fewer degrees of freedom in lower dimension, which are already very interesting from a say a solid state physics point of view. And you build up, and then so that you do before you have 10 to the 5. When you have 10 to the 5, now what do you do? Well, so yeah, something that I think would be fun to do is we have this sense of how is the interior of a black hole encoded into its Hawking radiation at very late times. And the idea is we think it is. We think that if you do some very complicated operation on the Hawking radiation, you can affect what's going on inside of the black hole at space-like separation, and that's an illustration of the emergence of space-time. You're doing something that would not be allowed by the classical structure of space-time. And if you have enough logical qubits and you're clever enough, you can arrange to kind of get the part out of the interior that you affect outside of the black hole, just enough that you could actually see it from the outside and verify that you can really communicate at space-like separation by doing something exponentially complex. But you really got to work hard because it's exponentially complex. So you need to have it be just big enough that the effect is sort of detectable, but not so big that it's just totally impractical to do it. Yeah, but I don't know. I think that would be pretty cool. I mean, there are also things that are more mundane that you could do first, but
so maybe Vlada, you can tell us the more mundane.
I wanted to say I do wonder about your 10 to the 5 logical qubit number because Craig Gidney just brought the number of physical qubits from Shor's algorithm from 10 to 20 million down to 1 million. We already know ways to bring it down to a few 100,000.
Yeah.
And so I have a strong suspicion that if one thinks carefully about it, one may be able to reduce that number further.
I mean, it's certainly possible. Like I'd want to do 100 by 100 matrices. So that's 10,000 degrees of freedom, I guess. And so to simulate 10,000 degrees of freedom for a decent amount of time, I don't know.
Can I ask a follow-up question to you, Dan? I get asked this question. I have no clue about the answer. If quantum computers, will it ever help us quantize gravity?
Well, yeah, that's the hope, right?
But so the black hole is one piece of it. But what about actually quantizing sort of a metric, for example, or
yeah, so you could see that by doing this simulation. So the theory I want to simulate is the workflow here is somebody proposes a theory of quantum gravity, and by definition it'll be some strongly interacting mess. And so we want to see, does space-time indeed emerge from this model that we can't solve? And right now we just sit around and say, I wonder if it does. Okay, but with the quantum simulator, we could just go, plug it into Mathematica and see, right? And so that's very useful if you're a theorist to have a way to see whether the theory works. Now, there's a separate question of is it actually the theory that describes our world, and that's a much harder thing to get. But right now we have 0 theories that describe our world. So if we can get one that's consistent with our world, that's already great. If we have 2, then we need more experiments.
Yeah. So maybe one question for Vlada. So you mentioned at the end this fantastic work with machine learning to find the correct parameter to control your experiments. But I think some of the students might be worried, but you say, oh, I'm substituting students with a machine. Where do you see this interface, and why will you bring us for this?
Oh, my students love it, right? Because they don't want to do the grunt work. It's a little bit like in biology, right? You don't want the students and postdocs be filling pipettes or whatever they do in my crude view of biology. And similarly, the students run it. They now turn the machine on at night, program it, and then in the morning they have new results that they can actually analyze. So it speeds up progress. It's just another tool, just like Mathematica is for.
So no substitution for grade. So what do the graduate students do then?
Well, one of the challenges with machine learning is, for instance, what do you learn from it other than the sequence that actually works? Can you, derive principles from it? And we find from systems we understand that machine learning rediscovers some rules or some ideas or some inventions that we have had before. Other things we don't really understand what it is doing, except that as humans we like to think in adiabatic processes, whereas these machine learning approaches, they don't care about doing bang bang kind of going very far away from equilibrium and then somehow back in some way that we don't understand. So I think there's a lot of interesting things to discover, and I think it makes student life better, not worse.
Do you think that either quantum computing or machine learning will help in finding some more gravitational ways or better ways to finding them?
I actually think yes. And I think the gravitational waves part I'm not so sure about, because they're intrinsically, at least the kind we look at, are very classical. But our instrument is completely quantum. And so is that going to be a time when we will have an algorithm like Vladan's that helps us come to some lower noise state? That absolutely, I think that will happen. And the more we're limited by just the quantum fluctuations, the more I think quantum algorithms will be helpful to get us there. So how do you again, these instruments have over 1,000 control loops and degrees of freedom. So how do you optimize for the one thing you're looking for? Right. Yours were 45 degrees of freedom?
Yes.
How nice.
Nice.
Yeah.
So let's see if there is some question from Ike.
One of the startling things maybe of this field was the introduction of a new idea from computer science, which was error correction into physics. And that technique of controlling entropy was very important for all three of you. Do you foresee other ideas of computer science, mathematics, and algorithms which you look forward to coming into physics that would also revolutionize physics in new directions?
I mean, for computing, maybe Harry Zhu would be the right person to answer. I think the question of how the architecture of a quantum computer, what does it look like? How much can we learn from classical computers, and in what way does it need to deviate from a classical computer to unleash its full power is a very interesting one, or how to interface them with classical computers, because I agree with, some speakers said it before, it will be some kind of hybrid system where it will be a quantum coprocessor together with, maybe GPUs and CPUs and other systems. And there I think we have a lot to learn from computer science, for instance.
Yeah. Ike, if I may add, I think in many of our experiments, we also really struggle with far from equilibrium systems, especially when there's dissipation. And I think the kinds of things that Sun Wan talked about will also be very important when we're really trying to optimize in the quantum regime for dissipative systems. So I think that's going to be important as well.
Paula? Sorry, we have questions coming in being moderated. So perhaps for Daniel. Hi, Daniel.
Yeah, hi.
Firstly, where do we get the Mathematica quantum plugin? No. So specifically on error rates and error correction, one thing that has been key for me with QPUs today has been the errors with patterns you can cancel out like wave functions. How much longer do you think such techniques will be relevant?
Well, I'm not sure if I'm the person to answer that question. Yes, I mean, certainly codes are getting better all the time, right? I mean, I think the only thing I'll say is that, quantum error correction was invented 30 years ago, but we still don't really have a good code that does everything that we want. The things that people use are sort of patched together where you want to do the surface code, but then you need to do magic state distillation, and the rate is good against some kind of errors and not other kind of errors. And so I'm not close enough to the weeds to have a great sense of how much the phase space has been explored. I mean, these LDPC codes that somebody mentioned, maybe I forget who mentioned, one of the first speakers. Jeffrey, maybe. Yeah. Jay. Oh yeah, Jay Gambetta. Yeah, that's right. I mean, that was a sort of fairly new idea that I think took a bunch of people by surprise, which is encouraging that we haven't equilibrated on coming up with new error-correcting codes yet. There are also these codes that come out of thinking about black holes, and maybe those will end up being useful too. I don't know.
Okay, I think that we are out of time, so unless there is one last pressing question.
Great.
Okay, so I'd like to thank the panelists again.
Thank you, Bella, and thank you.